This is a PowerPoint presentation to discuss the population of the NASIS database. And what we're going to cover here is a guide to the precision, the accuracy, and significant figures. Let's take a look at these databases that we deal with. The first one is NASIS. NASIS is considered an estimated soils property database. Why do we consider it estimated? Because we have an entire component population that we have to be able to estimate what the soil properties are for anywhere in that given population of that named component. The PETON database. It is also an estimated soils property database. Yes, I realize you can go out there and measure the color. I realize you can probably measure a few other things, but when you go to texturing, you are estimating the texture. And along with that, if you happen to estimate the clay content, that is what you're doing, is estimating the clay content for that given point. The National Soil Survey Lab, though, whenever we take a sample of that PETON and we send it into the lab will then analyze it based off of their procedures, and they will then populate the National Soil Survey Lab database with the results of those lab procedures. Let's take a look at the data that we happen to collect as soil scientists. We spend a lot of time gathering this data. First of all, look at the transects. Our transects are designed to provide us an estimate of the composition of that particular map unit. Textures are also an estimate when we're out in the field and we're doing a hand texture. That gives us the ability to estimate what the particle size distribution is of that particular sample that we have in our hand at that time. We also can take that information and send it into the lab, and we can have the lab confirm what we estimated in the field. We have field estimates and we have lab analysis, and we combine those together to provide us the information that we need about that particular soil to be able to populate the database. So now you've gone to the field and you've collected some point data. It could have been a PETON, it could be a transect, you could have characterization data. What are some of the important data that's collected? Well, the first thing you have to take a look at is the measurements that we collect. And each one of these collections is considered raw data. And so if you've gone out and you've collected the hand texturing of 15 points and you estimated the clay content at all of those 15 points, now you have 15 sets of raw data that has to be analyzed. And so all of this data that you collect is going to have some degree of uncertainty attached to it, whether it be a transect for composition, whether it be a hand texture, whether it be an estimate of KSAT. They all have a degree of uncertainty attached to it. And a case in point, I'll give you an example with a thermometer. A thermometer, everybody assumes that 98.6 degrees Fahrenheit is the temperature of a normal human body. But there is a degree of uncertainty in using that particular instrument. And typically on a thermometer it's 0.5 plus or minus. And so that means that the temperature that you're reading could literally be anywhere between 98.6 minus 0.5 or 98.6 degrees plus 0.5. So when you start looking at uncertainty, you have to realize that uncertainty is the measurement of it's determined by the scale of the measuring device. The uncertainty is the amount of variation that can be found in that measured value. It does not imply that there's a mistake in your results, but it just simply is the natural spread of values of a repeated measured quantity. That's all it is. What is the uncertainty in estimating clay content by an experienced soil scientist? Let's take a look at the number of people that can go out there and estimate it. We have different methods or different forms of uncertainty. The first one being the resolution uncertainty. And that is, how fine is the scale on the measuring device? Well, your measuring device is a thumb and a forefinger. And what we have to do is, okay, what is the resolution uncertainty on how well you hand texture? An experienced soil scientist can estimate the clay content within about 3%, 3 to 5% of the analyzed clay content. The calibration uncertainty. How well does that measuring device conform to a standard? And this is the one I really like, calibration uncertainty. Would that be like a young soil scientist versus an old soil scientist? Because an old soil scientist probably has his fingers a little bit better calibrated than what a younger one would. And then we have a reading uncertainty, and that's how well did the operator use the device. Basically, when you're reading measurements off of a particular gauge, how well does that person read that measurement every single time? Or in our case, is our reading uncertainty, is he missing a finger or something? And every time he pushes, he might be missing something there. But the point is, we've got different degrees of uncertainty here, and so uncertainty comes to you in many different forms: resolution, calibration, and reading. We're going to cover something here that everybody's aware of: precision. And precision is a measurement of how closely a group of measurements agree to one another. Basically, how reproducible are they? How close do all of these measurements come together? A close agreement translates into a very small uncertainty. However, precision does not mean that the measurements are close to the true value. We've all seen these bullseye charts before to try to explain what precision happens to be. The true value here is that bullseye, and you allow somebody to shoot 4 bullets. The lower left-hand target is a precise, very precise grouping. However, they all fall in a small area, but there's a small uncertainty. They can be repeatable, but it is certainly not an accurate shot. Let's take a real-world example here, and let's consider the precision of the sand, silt, and clay values that you collect. This data is collected via field hand-textured estimates. It's also collected using the field lab hydrometer methods and through the analysis through NSSL pipette method. So which method is going to have the greatest precision? Let's assume we got 10 soil science texture in a sample, or we have a sample run in the lab with 10 repetitions. Which method is going to have the greatest level of uncertainty? That's the key here. Take a look at just the estimates between what we could have come up with as a group of 10 versus the estimates or the actual results through the pipette method. Okay, we covered precision. Now let's take a look at accuracy. And accuracy is how closely the measurements agree to the true value. And remember what the true value was. That's the bullseye. So the accuracy is a measure of a deviation of the measured value from the true or accepted value. What's my percent error? So when you look at this true value, which is the bullseye, what can you say about the following measurements? And you know as well as I do, each one of these bullets represents somebody's attempt to hit the bullseye. And of course you realize that the lower right hand corner, we've got a great deal of accuracy. It's hitting right on. Well, we've covered precision and we've covered a little bit of accuracy. Now then, let's take a look at the methods that we use and determine which one of these are our true value. What can you say about the accuracy of the soil scientist estimates, whether they be a hand textured or whether they be a hydrometer jar method? And contrast that to the method that we use in the lab and the pipette method. So now, as we've already stated, there's a degree of uncertainty in all of our data. And that's the thing that we have to consider. And one of the ways that we identify that degree of uncertainty is through significant figures. And what we're going to do is look at how significant figures are used in our data to be able to use as an indicator of the uncertainty of a measured quantity. In order to understand significant figures, you have to understand the rules. The first rule is that non-zero digits are always significant. 1.24 meters, or that happens to be 3 significant figures, 1, 2, 4. The second rule is that leading zeros are not significant. So when you count the number of significant figures in 0.004212, you have to use the 4212 or 4 significant figures. Embedded zeros are significant, so 205.01 has 5 total significant figures. Trailing zeros behind the decimal point are significant. So if you come in here and put in 2.500 meters, then you have added 4 significant figures to this value. The trailing zeros in front of a decimal point, well, we can't really tell. So we don't know if it's 1, 2, 3, or 4. But these are your 5 rules for adding significant figures. Well, we now have to manipulate our significant figures. And in addition and subtraction, whenever we add or subtract numbers, we round the result of the calculation to the same number of decimal places as the number with the fewest decimal places used in the calculation. So we've got 16.54, 8.269, 0.47, 21.1. When you add that figure up, you get 46.379. However, 21.1 has only one decimal place, so therefore we have to round our 46.379 number to one decimal, and that gives us 46.4. Now, with multiplication and division, we have to manipulate the significant figures by identifying the number in the calculation with the least significant figures, and that answer will always have the same number of significant figures. So 65.64 times the total of 32.787 plus 98.443 divided by 56.4 is equal to 152.729,383. 56.4 has 3 significant figures. That's our smallest number with significant figures. So then we have to round off 152.729,383 to 3 significant figures, which causes us to round it to 153. That's our answer. Let's talk about rounding your data. When the result of a calculation has too many figures, and that's normally what happens whenever you use a calculator, you may need to reduce that number of figures that appear in the answer so that it becomes both meaningful and acceptable. For example, you've gone out to the field and you've hand textured your sand contents in addition to your clay contents, and you're asked to provide a mean sand content. And so you enter all of your data into the calculator, and you've put in all of your integer fields, and the result from the calculator comes out to 22.06465, whatever the heck it might be. It'll run out as far as it can on the decimal places. Now, what you have to realize is your significant figures of all your raw data is only 2. You have 2 digits, 2 significant figures, even though the result is 22.06465. You may think that it'd be best to round that off to 22.1, but you're carrying 3 significant figures, and you're breaking the rule of significant figures by doing that. You have to go with your lowest significant figure, which is 2. Therefore, you round your 22.06 down to 22. This process of reducing your numbers is called rounding the number. And when a calculation has a number of steps, you don't want to round each step. You want to round at the very end of your final result. Now, we're often going to collect 2 or more sets of data that are going to be needed in a calculation for a final result, and we're going to have to combine uncertainties when we do this, meaning field estimates and lab results. Uncertainties in measured or calculated quantities are quoted in a number of ways, and if the quantity measured is a volume, let's say, its uncertainty could be quoted as delta V. The uncertainties in each one of the pieces of data are going to impact the final result in the process, and this is called error propagation. So there's some mathematical operations that have to be considered here. And on sums and differences, what we're looking at is if the volume is equal to A plus B, or the volume is equal to A minus B, then the delta V is equal to the delta A plus the delta B. In other words, the uncertainty in the volume is the sum of the uncertainties in the A and the B. But if you're looking at products and quotients, if the volume is equal to A times B, or if the volume is equal to A divided by B, then the delta V over V is equal to the delta A over A plus the delta B over B. In other words, the fractional uncertainty in the volume equals the sum of the fractional uncertainties in both A and B. So let's take a look at your data selection, because this is something that a lot of you struggle with. A vital question for everybody that asks is, are all my data equal? A lot of the soil scientists, all their data is valid and none of it will ever be rejected. Others may look at it, a single set, and they'll label it as a incorrect set of data, and they'll throw away all that data set. And then there's other ones that'll even look at the individual key points and they'll reject those and keep the rest of them. And that's the things you got to look at. Now, you have confidence in your correctness of your experimental data really comes when you're satisfied with the experiment is repeatable. And what that means is, are you satisfied with how well you texture with your fingers, or how well the pipette method is being used? If you do have some suspect data points, then the best thing to do is to repeat the experiment. Of course, it's not always possible. Sometimes we didn't collect another sample before we buried the pit, so that's okay. But then there's other situations where the data point may be neglected or just flat rejected. For example, if there's a series of events that have to be hand timed, like doing an amusometer, and the operator loses concentration during one of those events and he skips a reading or he misses the readings, those are going to be some of the things that you have to take into consideration. There's a lot of statistical tests that'll help you eliminate spurious data when they do exist, but the rigid and unquestioning application of all data may mask a trend that you should know about. So be very careful about your data selection. So now, why is all this being explained to you? Well, the reason why is because we collect data from various sources. We estimate it and we also analyze it. And when you start looking at your data and analyzing all of this data that you've pulled together, you have to identify what is the precision. You have to identify what's the lowest significant figures that you're going to have in this raw data set, because that's going to control what values you populate into NASIS. Case in point, everybody that's listening to this has probably come in and used the estimated clay content, and they've also looked into the lab data and they've looked at the lab content, and so they may have estimated 36% sand while they were, or pardon me, 36% clay while they were in the field, but the lab results showed 38.3. We've all done this, but what is your lowest significant figure of the data that you're using? A quick review of the data that we've got available to us. We can very easily come to an agreement on what is a good estimation of the data that we should populate into NASIS. But when you start looking at bringing in two different sets of data with two different sets of uncertainties, you have to look at your significant figures. And if you're out there collecting data and using that data for analysis that's at an integer level, and you're using data that's coming from the lab at a decimal degree, then then you need to consider your significant figures. And in this case, here is an example where somebody has gone in and populated the database with a decimal when their lowest significant figure is 2. And the answer should have been left at 34, not 34.3. We can carry this precision one step forward, and we can look at the precision of our map unit composition. Remember, there's a degree of uncertainty with all the data that you collect, and that has to be considered when you populate the database. And so if you take a quick look at some data and you say, hey, wow, we've gotten to the point we can populate 56 as an RV for our component and 31% as an RV for another component. What are you implying to the customer here? What is your degree of uncertainty in that number of 56? What is the precision and the accuracy of reasonable soil survey practices when you consider the entire population of that map unit? How accurate, and what is your degree of uncertainty when you're populating 56 and 31? So what's the take-home message here? The take-home message is that NASIS data is an estimated soils property database. and it contains estimated properties of our components and of our horizons. And those estimates are based on an aggregation of all the point data that we have collected. Please do not populate the NASIS data with more precision or more degree of certainty than what your data allows.